Everybody, this is our last lecture for chapter 15. So let me go ahead and share my screen. When we're talking about chapter 15, we're talking about chi-square analyses. There's two different types of chi-square that you'll learn about in this chapter. We're going to talk about a chi-square goodness of fit, and we're going to learn about a chi-square test for independence. When we talk about a chi-square goodness of fit, it's very similar to a single sample T in that we're comparing a sample to a population. And so we have two different purposes for it, and I'll show you those. But we're looking at sample data to draw conclusions about a population, or we're looking for differences in a nominal categorical dependent variable, and we'll talk about that a little bit. For instance, I might want to look at your preference of cupcake. Do you like chocolate or vanilla? And you're going to say which one you prefer. I'm going to keep a tally of the preference, and I'm going to look at and see if that in the sample, that distribution is similar to what we observe in the population. A chi-square test for independence is a little bit different. It's actually looking at two variables, and it's wanting to see, are those variables independent of one another? So some people look at it similar to an independent measures T. I think it actually resembles more of a correlation, or it kind of reminds me of when you do a two-way ANOVA, looking at that interaction of variables. And that's how I conceptualize it a little bit better in terms of the test for independence. But we really want to see, is there a relationship between two variables? So couple different questions. We need to go back a little bit and talk about the fact that chi-square is what we call a non-parametric statistic. So we want to differentiate between parametric statistical techniques and non-parametric. Everything that you've learned so far has been parametric techniques. All of our t-tests, our ANOVA, even our correlations have been parametric. Those rely on population parameters. So they're requiring you to make assumptions about the parameters, either assumptions of normality, assumptions of independence. But when you violate those assumptions and your data set doesn't align with that, now the credibility of our conclusions is in question. So what we might want to do then is switch to using a non-parametric statistic that does not rely on those assumptions about what the corresponding population looks like. When you do parametric statistics, they require a numerical score, often scale variables. So our independent or grouping variables are often nominal, but then our measured variables that we're statistically manipulating and using for our calculations are typically interval or ratio data. So what we do is we manipulate those numbers, and I don't mean manipulate as in fake or in any way try to misrepresent, but what I mean is we move them, we do calculations with them, we add them, square them, multiply them. We're doing something with the original raw scores in order to calculate our measures of central tendency, our measures of variability, and then we're integrating additional calculations on those measures in order to apply our formulas. So we are depending upon interval or ratio data that we can manipulate for our calculations. In non-parametric statistics, that's not the case. They are what we call distribution-free tests. So we don't have any corresponding assumptions of what the distribution looks like in the population. And consequently, we're not relying on parameters. That's why they're called non-parameters. Remember, parameters are statistics that correspond to populations. Since we're not making any assumptions about the population, we're not relying on any distribution for the population. We don't have any parameters, so they're non-parametric statistics. Our hypotheses is not stated in terms of the parameter. Thus far with hypothesis testing, always learned our null hypothesis is stated in terms of parameters. We state that there's no differences are expected in the corresponding population, not in our sample. And so we're typically making really little to no assumptions about the parameter or about the population. And so that's why we don't don't write our hypotheses in terms of the population. With non-parametric stats, we're not limited. We can do a non-parametric technique with just nominal or ordinal data. We do not need ratio data or interval data, so we don't need scale data. We're not calculating means or anything of that nature. In our case, we're going to rely solely on frequency. So just counts. How many times does this particular data occur in our sample? How many people prefer chocolate versus vanilla? And we're just keeping tallies, those frequencies. Sometimes we may originally start out with numerical data that is scale data, like let's say age, right? But then it violates some assumptions. We don't meet the criteria. We can't use that parametric technique. So there are instances where you might convert that scale data into categorical data. Like we might say early adulthood, middle adulthood, late adulthood, and we're going to group you in categories, and we can run a non-parametric technique for that. But very rarely, most often we want to keep data in its original form as best as possible. And we almost always, if we have the ability to collect scale data, we collect it. So let's talk a little bit about situations when you may want to change that numerical or scale data into categorical data. Sometimes it's just easier, you know, we can't quantify low, medium, or high, but it might be just easier to collect data in terms of categories. Additionally, as I mentioned earlier, we may have violated some assumption that's necessary for that technique, and so we have to turn around and convert to a non-parametric option, which doesn't require assumptions of normality or homogeneity of variance or anything like that. Maybe there is a really high variance in our original sample data, and so the standard error is so huge, like we're never going to be able to find significant differences even if they exist, so we might want to lean toward doing a non-parametric statistic. And sometimes, like if you're trying to count the number of seconds it takes for a rat to finish a maze, let's say, and there's one rat that never finishes the maze. Well, that's an infinite number, and so we can't quantify that. And so in that case, we might want to use non-parametric techniques. Okay, so let's get into the goodness of fit. Remember, we have two different types of chi-square. One's a goodness of fit and one's a test for independence. When we're talking about a goodness of fit, we're using sample data and we're testing hypotheses just about the shape or proportion of the population. We're not making assumptions about the population. We're just testing to see, does our sample proportion match up with our population proportion? That's it. No assumptions of normality. So we look at how well does the sample fit. If you imagine it as a shape, that shape of the population, if it's a puzzle piece. If it's a good fit and the sample aligns with the population shape, great. If it's not, then we know that something else is going on here. So we're looking at research questions where we're relying on frequencies, right? We're relying on descriptors. We're not looking at means or standard deviations or what the typical score looks like in a group. We're really looking at counts. Kind of think about this as the democratic technique. It's a vote. It's boiling down to votes. Who got the most votes? So it's popular vote. Maybe we're looking at female lawyers compared to males. If the population, the gender distribution in the population is 50-50 or about 51-49, then we should see about 51 lawyers for 49, or 51 male lawyers for 49 female lawyers. We should see a 50-50 split, but we don't see that. We see males are more likely to be attorneys, and you know, we have, you know, people say we've achieved equal rights, but we haven't. We don't have, how many female presidents have we had? How many have we had? How many female senators do we have? How many female congresswomen do we have? We do not have equal representation in positions of power. So therefore we have not fully achieved equality. Which Coke do you prefer, Pepsi or Coke? My kids are divided. Some prefer Pepsi, some prefer Coke. So we can look at in a sample, hey, which do you prefer? and we can compare that to, does that align with the population in terms of sales or preferences? And maybe that tells us in our region, maybe it would be better to contract with Coke over Pepsi, right? Based on what our results suggested. Or what is the increase in proportion of college students declaring a business major over the last 10 years? So if we've seen business has grown overall throughout the nation, what about at any specific college? Is it matching that growth in the corresponding population? So when we're looking at a goodness of fit chi-square, we have to do a frequency table. We are going to literally count how many occurrences we have of any data point in our data set. And we also will do a frequency graph. Now, when we're talking about nominal or categorical variables, we're talking about bar graphs, right? So you're most likely going to see a bar graph, not a histogram with a chi-square analysis. And so we do our frequency on the y-axis and our different categories on the x-axis. And here we see in this particular data set, 5 got A, 11 got B, 16 got C, 6 got D, and 2 got in E, whatever that is, right? And so here's a frequency table. Here's most often the way that you're going to draw it out when you're doing a frequency table for a chi-square. It's most often in this matrix form, but our frequency table that we're familiar with, and then our frequency graph that we're familiar with, okay? When we talk about a null hypothesis for a goodness of fit, we expect that there would be no differences. The sample would match the population. So if we're talking about our lawyers, right, and we're saying, okay, our female distribution in attorneys should be equal to that in the overall population. So the null would mean that it's 50-50. They're equal, right? We're not seeing differences. Or are we seeing gender differences in the legal field? Then when we're talking about differences among categories, right? We're going to see if we have 4 categories that there's going to be a fourth, a fourth, a fourth. They have no preference. So we really do a goodness of fit in 2 different ways. Number 1, we talk about there's a no preference. And so we expect equality across all the categories. Whether we have 2, 3, 4, 5, 6, it would be 1, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. Or whether we're expecting no difference between a sample and a population. So if within the population, 28% of the drivers are younger than 30, then we would expect that people that get tickets, 28% would be under 30, because this is proportional to the population. Or 72% are older than 30, so we would expect 72% of tickets to go to people older than 30. That's not what we observe. We observe more tickets going to younger drivers. Is it because they're bad drivers, or is it because they're targeted? Probably both. I want you to know this is the basis for a Black Lives Matter argument. When we're talking about looking at the proportion of Black individuals killed in the hands of police. Number 1, they're arrested more than their corresponding population. So they're overrepresented in the people that are questioned, the people that are taken into custody, the people that are arrested and charged and convicted even. So they're overrepresented in those groups. Additionally, when we talk about the risk of them being murdered at the hands of police, they are disproportionately murdered. Their sample and population do not match. They have much higher rates of deaths in custody than corresponds to the population of Black people in custody or the corresponding population of Black people overall. So they are disproportionately at risk of being killed at the hands of police. You can do a chi-square analysis with the data in any major city and find that to be the case. Okay, so let's talk about what we do with the data. We already mentioned that we collect frequency data, right? Well, that frequency data that we collect from our sample is what we call observed frequencies. The observed frequencies are the actual raw data that we get that are observed in our sample. So this is of the total number of participants, what what frequencies did we observe in that sample. We're not necessarily breaking anybody into groups, right? We're not doing that. We're just looking at who reported chocolate, who reported vanilla. Did you or did you not get a ticket, and what age group are you in? That's it, okay? Expected frequencies are based on the population. We expect the distribution to be X, Y, or Z, right? So if there are 28% of the population under 30, then our expected frequency for the sample of people getting tickets should be 28%. So if we have 100 people, we would expect 28 of them to be under 28, and we would expect the others to be over. Okay, so when we're talking about expected frequencies, we kind of need, they are used to determine our null hypothesis, right? We would expect the same distribution to occur in our sample. And so in this particular study, it's suggesting that in the population you have 25% in category A, 50% in category B, and 25% in category C, okay? So we have a total of 40 participants. So we need to determine what our expected frequencies are based on that population, right? So if in fact our sample matches our population, then our expected frequency of 40 people, 25% of 40 is 10. So of those 40 people, we expect category A to have 10. We expect category B, it's 50% of 40 to be 20. And category C should be 25%, which is 10. So looking at this, if you add up your expected frequencies, 10 plus 20 is 30, plus 10 is 40, they equal your N. So you calculate your expected frequencies based on the proportions that are being observed in those categories within your population. Okay, and then what you do is you compare these expected frequencies to the actual raw frequencies you observed in your sample, and you see if they fit one another or if they're out of proportion and there's a significant difference. So when you do the chi-square analysis, here's one simple formula. So the trickiest part is calculating your expected frequencies. You have to make sure that's accurate. After you've done that, then what you do is chi-square, so we symbolize that this funny little X is a chi. Chi-square equals the sum. You take your observed frequency minus your expected frequency squared. You do that for every category that you have. So category A, you take your observed minus your expected, square it, plus your observed for category B minus your expected for category B, square it, plus your observed for category C minus your expected for category C, square it, okay? Add up all those and divide by the expected, oh, excuse me. So you don't add up all those first. First, you take your observed for category A minus your expected for category A, square it, divided by your expected for category A. And then what you end up doing is adding all of those results. And that gives you your chi-square. So again, the first step is find the difference between observed and expected, square that, divide it by the expected, and add the values. And we'll do a sample here in just a bit, okay? So a chi-square is essentially looking at the discrepancy between observed and expected frequencies, where observed are the actual raw data we get from the sample, and expected are determined based on the population, right? Or based on an assumption of no differences, a null hypothesis. So either we're saying there's no preference, so that all of the categories should be distributed equally, or we're assuming that we're comparing them to the population, okay? When we reject the null when there's small discrepancies, or when there's small discrepancies or no discrepancies, right? Then we say there is a goodness of fit between the data and what was expected in our hypotheses. And so actually we retain the null. Large discrepancies between the large discrepancies, we are going to actually reject the null. So the null is going to say there's no differences between our sample and our population, and the alternate is going to say we expect it to differ, okay? Okay. So the chi-square distribution, just like our t-test, we have a chi-square distribution as well, our z-score distribution, which is our unit normal table. There's also a chi distribution, and that's going to be in your appendix. So let's go ahead and go there now. I don't have that open, so bear with me while I find it, okay? I'm going to stop share. I'm going to get out of here for just a second. And here we go. I'm going to share again. When the PowerPoint's going, it kind of locks me in, so I'm going to share again. Okay, so I'm in our module. I'm in our course. I'm going to go here to the Appendix B. And then when you download that, you're going to see unit normal table, t-test, F distribution, and then here's actually the critical region for the Pearson product moment. And then now we're going to go to a chi-square distribution. So with the chi-square, we need to know our degrees of freedom, and we need to know what our alpha level is that we're using. So what proportion are we expecting in the critical region? Okay, and so let me then go back to our lecture. Okay, so we are looking for, in the chi-square distribution, if you have, it's assuming null hypothesis, right? And it's a theoretical distribution. We're using it just like we would any other distribution. I want you to take note, it's a positively skewed distribution, so all chi-squares are either 0 or greater. We don't have any negative values for chi-square. If you do, you did something wrong. When null is true, then you're going to expect the observed frequencies to align, so there aren't discrepancies when the null is true, and you're going to expect really small chi-square values. So just like everything else, the bigger the d, the better, the bigger the t, the better, the bigger the f, the better, the bigger the chi-square, the better. Bigger chi-squares are more likely to mean that they're in the critical region, and we're going to reject the null. Okay, so as noted in the appendix, this is our distribution of the chi-square. It's only a positive distribution. Our critical region is in that tail end. It'll be a smaller tail if you're using a smaller alpha level. And then the higher number of categories kind of change the shape of your distribution a little bit. You're going to have bigger chi-square values for bigger degrees of freedom. So larger samples will be associated with huge chi-squares sometimes. We typically don't see z-scores that are 40, but it wouldn't be uncommon to see a chi-square that's large like that, okay? When we're calculating degrees of freedom, these aren't based on the number of participants you have, they're now based on the number of categories you have. So if we were looking at category A, B, and C, that's 3 categories. So we define category by the C, that's how we notate it. So degrees of freedom is categories minus 1, okay? And then additionally, just like always, degrees of freedom is kind of looking at which ones are free to vary when you're looking at the null. And so since you're measuring 3 categories, once your chi-square is known, 2 of them are fixed, right? Okay. Of course, the final expected proportions should all equal 100%. And again, chi-squares tend to be larger if you have more categories and more degrees of freedom. When you're talking about the critical region, again, we're going to go back to our appendix. And we are looking at, it's going to be affected by your degrees of freedom. And this, just like with the z-score, tells us what our boundary is. So if we have a chi-square with 21 degrees of freedom at an alpha level of 0.05, the chi-square needs to be larger than 32.67 in order to be in the critical region, okay? So as I mentioned, chi-squares tend to be larger and very different than z-scores, and they're only positive, okay? Okay, so let's go back. Okay, so let's do a learning check here. And I'm going to go ahead and write these down. I hate this example, just so you know. It's looking at orientation of pictures, a particular picture, how you hang it. What's the preferred way to hang it? And I freaking hate this, but you know, in the older editions, this is the sample that they gave us, so we'll work with it. And so this is what we actually have. We have a total sample of 50 participants. So if you add up all these numbers, it is 50, right? So 18 plus 17 is 35, plus another 15 is 50, okay? So these right here are the observed frequencies. When we asked 50 people how they would prefer to hang up this painting, 18 said top up, 17 said bottom up, 7 said left side up, and 8 said right side up. Now, if there was no preference and we had 50 people, we would just divide 50 by the 4 categories, and we would expect 12.5, 12.5, 12.5, 12.5. So our expected frequencies are different than our observed frequencies. What we need to do is we need to submit it to a hypothesis. So the first thing we're going to do is state our hypothesis. And we are going to, give me just a second. I'm writing this down for a second because I'm going to leave this and go to the work screen. So I need to know what our data is. So we're going to state our hypothesis and our alpha level just like anything else. We're going to go to our distribution table just like anything else and look up the critical region and that boundary. Then we're going to determine what analyses we use. We've determined it's a chi-square. So we have to first calculate what our expected frequencies are. Then we have to apply that to the formula, which requires our observed and expected frequencies. And then based on that chi-square, we determine is it in the critical region or isn't it? And we make a decision with our null, okay? Oops, oh, look, boom, it's already there for me. I don't have to go to the whiteboard, but I'm gonna go to the whiteboard for you, okay? So first thing is we have 50 people, 4 categories. I'm gonna go ahead and look up our degrees of freedom. So when we talk about degrees of freedom for a chi-square, it's categories minus 1. So it's C minus 1, which would be 3. We're going to use a 0.05. So our critical region is going to be 7.81. So now I'm going to go to our whiteboard. And I just want to put that over here, right? Our critical region, oops. If I really want to do this effectively, okay? Then it's a positive chi-square, right? It's just positive. So our boundary is 7.81. So we'll keep that in mind. We'll also keep in mind that we had 4 categories. We had our top up, we had our bottom up, we had our left side up, and we had our right side up. There were 18 people that had top, 17 bottom, 7 left, and 8 right, okay? Now, these are what we call our observed frequencies. Those are the actual frequencies we observed in our sample. Let's look at our expected frequencies. If we're assuming a no preference hypothesis, if we have 50 people, we have 4 categories, we just take 50 divided by 4, and that's 12.5, 12.5, 12.5, and 12.5. That's right up, left up, bottom up, and let me erase this mess right here. And this is top up, okay? Okay, now these are our now expected frequencies, okay? And what we're doing now is comparing our observed to our expected. So our formula for chi-square is the sum of your observed minus your expected squared, okay, over your expected. So we have to do that for each category. So we say this is the sum of this for category 1, top up, plus this for category 2, bottom up, plus this for category 3, left up, and then plus this for category 4, right up. So we literally have to calculate it. So let's look at first top up, okay? So the observed frequency is 18 minus 12.5 is the expected squared divided by 12.5, okay? And if I do that, it's going to equal 6.5 squared, right, divided by 12.5. I have to take out my handy dandy calculator. And first I have to navigate to it. There we go. And I'm going to say 6.5 squared equals 42.25 divided by 12.5, 3.38. Okay. Now I'm going to do the same thing for 17 minus 12.5. So now I'm doing it for the next category, divided by 12.5. That's going to be 5.5 squared over 12.5. And that is going to be my handy dandy calculator. 5.5 squared equals 30.25 divided by 12.5 equals 2.42. Now I'm going to do 7 minus 12.5 over 12.5. And that's going to be negative 5.5. Which is still, because once I square this, right, it's a positive number. So it's still going to be 2.42. And then finally, my last one is going to be 8 minus 12.5. And so that's going to end up being negative 4.5. And when I do 4.5 squared, that equals 20.25 divided by 12.5, that equals 1.62. So now I'm going to add up all of these values right here. And I'm going to say 3.38 plus 2.42 plus 2.42 plus 1.62 equals 9.84. So then when I go over here and I plot it, it's going to be probably over here somewhere, which means it's in the critical region. So I reject the null. And I say there was, in fact, a significant difference or a significant preference in orientation for wall hanging. And I'm going to report my chi-square equals 9.84. And I'm going to indicate my top up was the most preferred, followed by bottom up, then the right up, and finally the left up had the lowest preference in our observed sample. Make sense? Okay, so now let me go back to your lecture and we'll plug in the answers. Our null hypothesis is stating here there's no preferences. Our alternate hypothesis is saying, yeah, there is a preference in one or more groups. We're having an alpha level of 0.05 based on looking at our degrees of freedom. Category -1 is 4 minus 1 of 3. So that produced 7.81 as our boundary. We already know that because we did that. Then going through all the calculations, right? This is calculating your expected frequency. We just take our total n divided by the number of categories. They have 12.5 all the way across, okay? Then here's our formula. They're doing 18.5 divided by 12.5, blah, 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 for every single category, and they get a chi-square of 8.12. I don't know if our chi-square was exactly that. I may have done a little bit of math off, but that's okay. And then I say 8.12 is in the critical region, so we reject the null. And this is my statistical evidence, chi-square, comma, degrees of freedom of 3, comma, n equals 50, close parenthesis, equals 8.12, comma, p is less than 0.05. Does that make sense? And then let me take that evidence and then I will write it out in a sample. A sample paragraph for you, okay? Well, actually, I think I might forget that. I think I might just type it up. That might be easier. So give me a second. Let me stop sharing. Let me grab a Word document really quickly. Let me start sharing again. Here's my Word document. So what I'm going to say is there was a significant, and let me go ahead and I'm going to first of all make this Times New Roman because I'm, and then let me blow it up so you can see it. Okay, so there was a significant preference in hanging orientation for the picture provided. I should spell that right. So that's basically saying that there was a statement of significance. There was a significant difference. And I'm just going to use X for now, but I actually, let me see if I can insert my chi-square. It's not that fancy, but it's there. It depends on your font. And this is going to be a superscript. Okay, so chi-square, and now I want to take that superscript off. And we're going to do a parenthesis. Sorry, I need to take that superscript off again. Parenthesis, and we're gonna say how many, excuse me, how many degrees of freedom we had, and then our n equals 50, close parentheses, and our square equals 8.12, comma, p is less than 0.05, and I just want to italicize everything because that is appropriate APA. Oops. It's also, oops, sorry. It's also not good to break this up like that. So I'm going to hit return and keep it all together, period. And then I'm going to turn around and now interpret it, do my statement of interpretation. The most preferred orientation was top up. We can just do our counts, followed by bottom up, then by right side up, and lastly, left side up. Okay. So here is our template, right? Statement of significance, then our statistical evidence, and our statement of interpretation telling us what's the overall pattern with our descriptive stats and our frequencies. Okay, so that is your sample and what it should look like. And then the only thing I'm looking at here is in terms of spacing. I wouldn't want to have this space, right? I'd want to keep it together a little bit more. So I would want to change my spacing and remove that space after the paragraph. There you go. So there is your sample for a chi-square goodness of fit. Goodness of fit can be used for either testing whether the sample fits the population or whether or not there's a preference among the categories. We used a sample for the no preference. Okay, so now let's go back to our presentation. And here you see it in the literature, okay? Okay, now, moving on to looking at kind of in general, I don't know why that says times. I think it's saying, I don't think that's supposed to say times. Let me fix that because that's odd. I think it's supposed to be a single sample t-test, okay? So this is a non-parametric statistic where we aren't relying on any population data, no assumptions of normality, homogeneity, none of that. And a single sample T is a parametric statistic. It does make assumptions about parameters or rely on parameters in terms of knowing something about the population. It does assume that the population is a normal distribution, and then we are manipulating the scores. Specifically, we're calculating means and variances and manipulating that data within our formula. So we are very much using scale data versus us just over here in a chi-square, just using frequency data, okay? Okay. So now let's look at a chi-square test for independence. This might be a good time to go take a break, get a snack, go for a walk, do something that might get you up and running a little bit. break up the monotony. Even if you want to just stop right now and go do a couple problems in the book, that might be helpful. I am going to keep on going, and we're going to talk about the chi-square test for independence. When you're talking about a chi-square test for independence, you're looking at to see if two variables are related to one another, which in some ways sounds like a correlation. Some people relate it to an independent measures t, and I often think of it as an interaction, kind of like that ANOVA interaction that you're analyzing. It can be used for an experimental design. So you definitely can use it for a very controlled research study if you so choose. We're actually going to use look at an example of one of my favorite researchers who does it as an experimental method. And you have each person in the study is classified on two variables. So similar to a correlation, you get measurements from each person on two variables, okay? So you always have like a two-dimensional matrix that's formed. Again, this is why I often liken it to that interaction, because that matrix is always helpful, right? And we're still using frequency data. So we're just counting the number of people that fall within any category on that matrix. That's it. We use that frequency data from the sample to determine if there's a relationship. So the frequency data is used that we observe. We also, based on our total N, we can estimate what our we can't estimate, we calculate our expected frequencies, compare those to our observed frequencies, and then see if there is in fact a significant difference between the two or if the two variables are related. So here's an example. Elizabeth Loftus, who is a famous memory researcher out at UC Irvine. So if you have an opportunity to go to UC Irvine and you're interested in cognitive science at all, oh my gosh, she's incredible. She's a legend. So Elizabeth Loftus and partner Palmer did a research study starting way back in 1974. They started to investigate the suggestibility of memory or false memories. So this particular study, they investigated how eyewitness memory can be affected based on the types of questions that you ask. They had 150 students watch a film. The film showed a car accident, and then the participants were randomly assigned into one of three groups. The first group was a control group. They just watched the film and they were brought back later to answer questions. The other group was asked about how fast were the cars going when they smashed into each other, okay? So after they watched the movie, they were asked how fast were the cars going when they smashed into each other. The second group was asked how fast were they going when they hit each other. And then the third control group wasn't asked anything, right? So I basically am asking a question, but in a very different way. And I want to know if the way in which I ask a question influences the outcome, okay? 1 week later, they come back in and they're asked if they remember seeing any broken glass in the video. And what we're trying to see is their relationship with the type of question they were asked with how they respond to the broken glass. The broken glass is just a yes or no. So this matrix is formed down here where the broken glass, they either said there was or wasn't, and this is based on what group they were in. If they were in the group that was asked how fast they were going when they smashed, 16 said yes, there was glass, and 34 said no. So altogether, there were a total of 50 people in that group. Here we had another 50 people in the group that was asked about hitting one another, how fast they were going when they hit one another. 7 said yes, there was glass. 43 said no, so that's a total of 50. And our last 50 were in the control condition where they weren't asked anything. 6 said yes, there was glass, not much different than the ones that were asked if they hit one another. And then 44 said no. So what we want to know is this aligning with the expected frequencies? What would we expect in the expected frequencies? So the biggest trick here is determining what our expected frequencies are, okay? Remember, we had 150 people. Oh, this is, oh wait, I think I skipped. Oh, I didn't go through it. Okay, I will go through it. Remember, we had 150 people. 50 were in each group. And so we had two groups. We had yes, right, and no. And we had smashed, hit, and then control, okay? And if we had 50 people here, we would expect, if there was no relationship, 25 and 25, 25 and 25, 25 and 25. So 75 would say yes, 75 would say no. That's what we would expect if it didn't really matter, right? But we want to know, did it matter? So we would compare these expected frequencies to the observed frequencies and see if they differed, okay? And they did in fact differ, okay? So let's go to back to our lecture, and we're going to actually do an example together. So when we talk about a chi-square test for independence, we again have two different versions of what that might look like. If we're looking at evaluating the relationship between two variables, then our null is just going to be no, the two variables aren't related, and our alternate is yes, they are related. So this is more consistent with a correlation, right? We're not looking at numerical data. We're not trying to calculate a Pearson product moment R, no correlation coefficient, but we are in fact using frequencies to see if the two variables are related. The second way we can use the chi-square test for independence is when we're trying to look at, are there significant differences between the populations, okay? So based on are there significant differences between the people who were asked about smashing, about hitting, or not asked at all, okay? And that's more similar to that in either an independent t-test or that interaction of the two-way ANOVA. Does the effect, does their report for glass depend on what category they were on, right? And that's more like an interaction. So, however, we get to use frequency data, okay? So we consider the variables are independent from one another if there is no consistent predictable relationship, but if we can see that in fact being asked about smashing into each other produces a greater probability or produces them more people saying yes, they saw glass, then we know that there are in fact predictable relationships there, and therefore we reject the null, okay? Because a null is saying no, there's no differences between groups, and the alternate is saying yes, there are significant differences between groups, okay? Okay, so for both the chi-square and the goodness of fit, we always have to calculate our expected frequencies, always. And how we calculate the expected frequencies is we need to follow this formula right here. We take our, this frequency with the subset C is how many do you have in the total column, how many do you have in the total row, divided by the total that you have all together, and then we have that's our expected frequency. So this is a formula you can use because it can get confusing and complicated, especially the more categories you have, it can get really confusing, okay? So keep that in mind. I don't know what's going on with my presentation over here, but it's highlighting multiple things and it's being kind of weird. So I'm off a little bit, okay? Keep that in mind. Okay, so here we go. So now what we do is to calculate our degrees of freedom, it's going to be a little bit differently. So we're going to say degrees of freedom equals the number of rows we have minus 1 times the number of columns that we have minus 1. So here's our formula for a chi-square test for independence. And once we, even though we have a different formula for degrees of freedom, the formula for chi-square is the exact same. It does not change whether we're doing a chi-square test for independence or a chi-square for goodness of fit. Their formula is exactly the same, okay? Oh, it's making me so mad. Okay. So here is a learning check that's in your book. Older editions, not the newest, but 15.4 is the example. And it's looking at personality type and color preference. And personality type, either you're categorized as an introvert or an extrovert, and is there a preference color? Is there a red, yellow, green, or blue preference color? So do we see preferences in color based on your personality type? So the first thing we do is state our hypothesis and alpha level, right? We locate our critical region, which means we have to calculate our degrees of freedom. And we end up plugging that in and calculating it for our chi-square. And that first starts with calculating our expected frequencies and then plugging that into the formula. And then based on that, if our chi-square falls in the critical region, we reject the null. If it doesn't, then we fail to reject. Ugh. I'm getting frustrated because it will not advance. Okay, so let me, it's acting weird. So just bear with me, okay, because it's freaking out. I'm gonna stop sharing for a second and then see if I can get it back where I need it. It's being weird. I am not sure, but it's making me mad. I am not patient with technology at all. Okay, so let me see if I can share again. Let's see if I can launch it, if it'll let me launch it. And we'll do it that way. I'll try not to navigate between screens too much because it's being challenging. So here's our original data right here. And when we are stating our hypothesis, we're going to say the variable, or excuse me, the two variables are independent. That's a null. And our alternate is saying, nope, they're not. I don't think that's right. It's the opposite. We're saying that there's no relationship versus there is a relationship. They are independent or they aren't independent of one another. So when we say they're independent, we're saying there's no relationship. When we're saying they are not independent, we're saying there is a relationship, okay? So there are significant differences or there aren't significant differences. So calculating our degrees of freedom, we had, when we talk about columns, we had 4 columns, right? -1, and we had 2 rows, -1. So 3 times 1 equals 3. So the critical boundary when we go to, and I'm not gonna go there because the technology is being funky, but when we go to that chi-square distribution, we look up an alpha level of 0.05 and a degrees of freedom of 3, same as last time, our critical boundary is 7.81. Now we have to calculate our chi-square. The first thing we have to do is calculate what our expected frequencies are. Remember, here's the formula. Our expected frequency is the frequency for the column times the frequency for the row row divided by n. So in here, I'm looking at my frequency for my column, right? Times my frequency for my row. And so let me just be really clear. Here's our frequency for our column. If we had 10 introvert and 90 extrovert that preferred red, our frequency for our column is 100. If I have 50 introverts overall and 150 extroverts, my frequency for my row is 50 for introvert and 150 for extrovert. So when we're talking about those, we're taking frequency for column times frequency for row, right? So I need to know I'm right here figuring out this one right here for my red introvert. My column for red is going to be 100 and my row value for introvert is 50. So, and there were 200 overall. So 50 times 100 divided by 200 equals 25. Now for extrovert, I now have 150 in my extrovert row and 100 in my column. So 150 times 100 divided by 200 equals 75. Okay, do the same thing for introvert with yellow. I'm going to take my introvert of 50 times my row of 20 divided by 200 overall equals 5. Extrovert for yellow, I'm going to take 150 and 20 divided by 200 equals 15. Okay, so that's how we do that for each of them. So this now on the right becomes our expected frequency. Okay, the left represents how we calculated it. The right represents our expected frequency. Then we're going to plug all of this, right? Our observed is up here on the top. Our expected is over here to the right. We plug that in for each of the 8 categories, right? Because there's eight separate categories. So notice we have 1, 2, 3, 4, 5, 6, 7, 8 pieces for this formula, 1 for each category. And in the end, we get a chi-square of 40.8. See how large they can get? The more categories you have too can make it larger. But 40.8 is in fact way bigger than 7.81. So it is in the critical region, so we reject the null. And we do see that these two variables are not independent of one another, right? They actually do have a relationship, or we can say that the color preferences is based on your type of personality, where we see extroverts are significantly more likely to prefer red than we see introverts, right? Okay. Okay. So let's talk about how chi-square relates to other tests. Chi-square specifically for independence. Like I said, I see it more as, even though some people relate it to independent measures T, I see it more as relating to correlations. Are they related or are they not related? Are they independent or not? Obviously with correlations, we have to have scale data. And so chi-square gives us a little bit more flexibility, and we can just use frequency data. So we can do a chi-square analysis with only nominal or categorical variables. Or it's similar to me, although we talk about it in terms of a t-test or an ANOVA, I like to think of it as that, interaction in a two-way ANOVA, because we really say the effect of such and such of one variable on the DV is dependent upon the level of the other variable. That's literally how we interpret it. So I like to think of it as that, that interaction, okay? Okay, so when we talk about when we talk about an effects, or when we talk about a chi-square, we can see that they're related or not related. It's a good fit or not a good fit. But again, we need an effect size. So that's just the first step in finding significance. Then we follow up and do an effect size. And the effect size that we use for a chi-square is a phi coefficient, which you were introduced to that concept in the correlation chapter. Remember, a phi coefficient is when you have two nominal variables, and that's exactly what we have in a chi-square. So just like R squared can be used as an effect size for t-tests on ANOVA, R squared is also our coefficient of determination or our effect size for a correlation. Now another correlation is used as an effect size, a phi coefficient correlation for our chi-square. So here's the formula for phi coefficient. We take our chi-square divided by n, and the square root of that equals our phi coefficient, okay? If you have a large matrix that has a lot of different, this is great for just a small 2x2, but if you have a large matrix with a lot of different rows and columns and more categories, then we're going to use Cramer's V. And the Cramer's V is our chi-square, so that's always your first step, divided by n times degrees of freedom. This degrees of freedom formula corresponds to the Cramer's V, not to the chi-square, okay? So you're going to use either the smaller of rho minus 1 or C minus 1, okay? So rho minus 1 or column minus 1. Whichever one's smaller is your degrees of freedom for the Cramer's V, okay? Okay, and then when we talk about chi-squares, you know how we have assumptions for t-tests and assumptions for ANOVA. We look at assumptions of normality, that they're independent observations, they have homogeneity of variance, right? We have these assumptions that we put in place. We do have assumptions for a chi-square, even though they're not based on assumptions about the population. We do have assumptions that have to be met. First of all, every single count or frequency needs to be a separate person. You can't have one person giving you data in every category. They're either in one category or the other. If you have one person producing multiple responses, that's not a nominal variable, so a chi-square is not appropriate. Secondly, you need to have a minimum of 5 frequencies in each category. So your sample needs to be large enough that it's going to produce at least 5 frequency of 5 in each category. So a minimum. If for whatever reason you can only get 3 or 4 in one category, you need to increase your sample size, okay? So the test just it's very sensitive, and it only, it will not work if you have under 5, okay? So that's pretty much it for chi-square. Hopefully it's not too confusing. Most people kind of either like or don't like chi-square. I like them. I don't use them as much, don't see them as often in the literature, I'm being honest with you, but they can be pretty useful. And again, they often become our defaults. If we violate the assumptions in the parametric techniques that we're using, we can convert it over to nominal data, frequency data, and then do a chi-square. So I have a professor who preferred only chi-square. He did everything with chi-square. He almost never used a t-test. Everything was chi-square. So otherwise, I hope that was helpful. Let me know if you have any questions, and we'll look forward to seeing you back in class.